So chapter 4 is going to focus a lot on starting to do reactions. And the very first set of reactions we're going to do are going to be bromination reactions. And before we dive into bromination reactions, I want to take a second to talk about the three main types of reactive intermediates that we can have on carbons. So a reactive intermediate is going to be a species that's going to be generated during the reaction, and it's going to be a molecule that is has some level of temporary stability, but is going to be still very reactive. I want to go to our final product, and we're going to be generating these reactive intermediates, and the stability of the reactive intermediate is going to have a big impact on our reaction conditions and the reaction progress and things of that sort. So in general, there are going to be three different types of reactive intermediates that we have: a carbocation, a carbanion, and a radical. And much like way back when we talked about hydrogen versus hydride, the difference between each of these is just going to be a single electron. A carbocation is going to be a carbon that has 6 electrons around it and has a positive charge. A radical is going to have 7, and then a carbanion is going to have 8. So the difference is just going to be a single electron between each of them. Now, a carbocation and a radical are going to be deficient. We know that carbon likes to have 8 valence electrons around it. A carbocation having 6 and a radical having 7 are both going to be examples of electron deficient. And this is going to be one of the reasons why they are so reactive. They want to undergo a reaction in order to gain those extra electrons to have a full octet. Now, there are ways that we can stabilize a electron deficient species, and these are super similar to ways in which we talked about stabilizing, for example, a conjugate base way back in chapter 2. Resonance and the inductive effect are 2 of them. Carbanions, which are going to be electron-rich species, they're going to have a lone pair, and that's going to give an sp3 hybridized geometry. They're going to be the opposite. They're going to be a little bit more reactive, trying to form a bond to help the formal charge. So to kind of show what each of these looks like, a carbocation is going to be carbon with a positive charge. A radical is going to be a single electron, and we show that single electron as just a single dot rather than a set of dots, so 2 dots being a lone pair. So a carbanion is going to have a lone pair, which would carry a negative charge. Because carbon wants 4 bonds, here it only has 3. And in each of these, there's going to be kind of differences in terms of their properties. Carbanions are going to be more nucleophilic. They have electrons. It wants to make a bond in order to get that 4th bond to have a neutral formal charge. So it's going to be more basic. It's going to be attacking. Where your carbocation wants to be attacked. It's going to be more acidic, more electrophilic. And with this, there's a big talk on the stability. And the stability is going to be a big factor. And this is going to kind of come from the idea of an inductive effect. So let's go ahead and think about radicals. And where do I want to put this? Let me pause for a second. So for radicals, the more stuff we can put around them, the more stable that they will be. So if we consider, for example, a skeletal structure, there's just like a butane. If you have a radical all the way at the end on the final carbon, this is going to be a primary. And our description of primary, secondary, and tertiary, which are the 1, 2, and 3 degrees, are going to describe how many bonds are kind of connected to it. So here we see that we have exactly 1 bond, that dotted line right there, and we call that primary. That is not very stable. If I have that same butane, but I put it on, for example, the 2 position, here there are 2 bonds which are going to it. We call that secondary. If instead of having butane, let's say I have another carbon connected to it, and then a radical, where it's kind of in this pocket there with 3, you have 1, 2, 3 bonds. We call that tertiary. The more stuff you can put around a radical, the more stable it will be. So primaries are going to be very unstable. Secondaries will be more stable. Tertiaries will be even more stable. We can also find other ways to actually stabilize a radical. One of the most common is going to be through resonance. And this actually has a specific name. So let's say I have a molecule here and then like a radical. This is known as allylic. And allylic species are ones that can actually do resonance. So I can actually show a resonance here. Just give myself a little more space. Where I have resonance structures of that radical being spread out across multiple different atoms. Even though that looks like a primary on the top and then a secondary on the bottom, that extra resonance actually makes it even more stable. So in terms of stability of radicals as well as carbocations, primaries not so good. Secondary is a little bit better because they have some stuff around it. Tertiary very good because we have a bunch of stuff around it. And then allylic being even better because we have the ability to resonate and really stabilize that not so stable original structure. And the more that you can stabilize it, the more likely you are to get a reaction there. So when we do brominations, which we'll talk about in a future video, we're going to try to find the location where you can generate the most stable reactive intermediate. Much like how we were trying to do, like when we were doing acid-base stuff, we were trying to find out like the most acidic proton is going to be the one that gives us the most stable conjugate base. Now, let's go and end there, and that'll be our kind of key summary of our reactive intermediates. So we have carbocations, carbanions, and radicals. We are going to focus a ton on radicals in chapter 4, and then we will talk about carbocations a lot in chapter 6 when we're talking about substitution reactions and the stability of your reactive intermediates, especially your carbocation and your radical, is going to be focused on surrounding them. Now, your carbanion is going to be the exact opposite trend, but the primary, not very stable, and primary means you just have one connection to it. Secondary will be more stable, and it has 2 connections to it. Tertiary has 3 connections and is more stable yet. And then types of radical are even more stable. Allylic ones are even more stable because they can do resonance. There is one other form, and it's known as benzylic. So if you have a benzene ring and then you have a radical on it, that is known as benzylic, and that's going to be even more stable. It's like an allylic where you can do resonance, but here you can actually resonate around the entire benzene ring, so you can draw even more resonance structures associated with it. So in terms of our stability, ignore that. So in terms of our stability for radicals, primary is the worst, secondary is better, tertiary is better, allylic is better, and benzylic is the best. So we'll go and stop there, and in the next video we'll start talking about some bromination.